Yeah, right.
Just sweat.
Yeah, I should invite him back because he's always impressed when it's hot in here. All right, so midterm exams. So overall performance I was really happy with. Okay, so I told the other class this also. This is the best that any 222 class has ever done on a midterm. The average was above 80, and it was the same difficulty, possibly a little more difficult than some of the other midterms I've given. So I think people are in the right place or moving towards the right place where they need to be with this material. It's an exam where you could get nickeled and dimed. There were some key concepts I was looking for, but there were also some details. And in some cases, if you got a lower grade than you were hoping, it's a lot of nickel and diming, which is unfortunate because that's not necessarily reflective of your understanding. And this has been a new experience for me also. I'm finding people who seem to understand the data structure part, but are having trouble with the C part in some cases. They seem to understand how nodes and linked lists point to one another and so on and so forth. But in writing code, I'm seeing mistakes that don't really have anything to do with data structures. They have to do with programming in C. That's a good thing and a bad thing. It's a bad thing because it pulls your grade down. But it's a good thing because if you can figure out those syntax issues, those algorithmic issues, right, it's not stopping you from learning the data structures part. And one of the goals in this course is to get comfortable with data structures so that when we go on to 223, we can work with those structures, we can learn Java, but we can actually be using these structures to do other things. In this course, we basically write programs that let you type in numbers and they get added to a list or put into a queue or things like that. It's not all that exciting, right? In 223, we'll be making games, we'll be making things with graphical interfaces, we'll make a chat program, we'll do a 20 questions program probably. So we're doing programs that actually do things, right? But we can do that because in 222 we figured out how to use data structures. So this is moving us into being able to build on what we're learning here. So if your grade was lower than what you were hoping, right, come and talk to me. And let's figure out what these details are that are causing troubles. And in some cases, I've seen particular things that I think can be corrected pretty easily. All right, so let's just run through this to get everybody on the same page. So question 1, you were working with a structure named data. It had 4 pieces: a character, a pointer, which was a string, a single character, an integer, and an array of integers. So part A wanted a structure statement to define this structure, which was a struct data. So the syntax is always struct, the name of the structure, a curly bracket, and then you basically define the variables that make up that structure. So a string is always a char star, and this string was called level, semicolon. A single character is just a char, and that was called xc. We had a single integer, which was called val. And then we had an array of 10 integers called stuff, so that's integer stuff 10. And there's your structure definition. So some people tried to do this. And that'll throw a compile error. It'll complain about not knowing what the size of level is. And when we call functions, if we're passing a string or an array, sometimes we define the argument as variable name bracket bracket, right? I prefer not to do that. If you want a pointer to a variable type, use the star notation because it'll keep you from getting into trouble with this. This is doing something a little different. And it turns out that if you put this statement at the end of your structure, it'll actually compile. But if it's not at the end, it'll complain that it doesn't know how much space you need for this, and there's things after it. And it'll get kind of weird on it. So don't do it like that. Do it as a char star. Your xc is just a single character, so that you do not want a star. Okay, a star makes it a pointer. It means it's going to store an address. This is going to store an actual character. All right, if you want to store 10 integers, it's got to be integer bracket 10. And this is confusing because sometimes we use 9, sometimes we use 10, right? The deal is, if you have an array that contains 3 things, these are the indexes of the 3 things in the array. But this is declared with a bracket 3. This is saying how many things are in the array. These are the indices of those things. Because the indices start from 0, the last element's going to have an index 1 less than the size. So if we want 3 things in our array, the last element's going to have index 2. But if you're told you want 10 things, it's got to be declared with a 10. But the index of the last integer would be stuff bracket 9. Okay, so that gets confusing, and it ties into like less than versus less than or equal to. And that's practice will make that less confusing. All right, part B wanted a statement declaring a variable named code of type struct data star. So declaration struct data star and then the name of the variable. And that's all you need there. And you could also write struct data star code. And those are equivalent because C generally doesn't care about spaces. But to me, this one makes more sense. The name of the variable I'm declaring is code. The type of the variable is struct data star, pointer to a struct data. When you start doing this, it starts to get a little confusing to me. Because my variable's named code, but I'm declaring it as code star. Yes. That makes sense, yeah. So if you wanted 2 variables, it would be struct data star code, comma star something else. Yeah, so that's the other way to look at it. That makes it less weird, I guess. But it still bugs me personally to think of it as star code, because then when you're trying to do something with code, there's a temptation to use star code, right, instead of just code, because that's what you call the variable. And sometimes that's the right thing to do, but for different reasons.
If you declare multiple, could you do, I don't know why you'd want to do this, but could you use space, like star space variable name for multiple ones?
Mm-hmm.
Just have a space between them?
Yeah, spaces are completely ignored. So you could say struct data space star space code 1, comma space star space code 2. That'll be perfectly valid. All right, part C, we want a malloc statement that allocates a block of memory large enough to contain a struct data, and then we want code to point to that block. And we've already defined what code is, right? It was a struct data star. So malloc, and we don't know how big a struct data is, so we use size of struct data. And we can set code equal to that. And here again, you don't want to say star code equals malloc, right? Code itself is a pointer. It's intended to hold the address of a struct data. This gives you an address in memory big enough to hold a struct data, so we're just saying make code point to that block of memory, set it equal to that address. If you said star code equals, it's going to try to find the thing that code is pointing to, which is probably null, and try to set that equal to this, and that's going to Seg fault. Do I have audio? Yeah, I do. Cool. All right, and then part D was the initialization. So we wanted to initialize the fields of code to these given values, x17, w minus 100, and these 10 numbers. So code is a pointer. So we find the thing it's pointing to with an arrow, and we can follow that with the name of a field. So code arrow level. And we can set that equal to W17 in quotation marks because it's a string. And if you like, this is also the thing to which code points, the field piece of it, the level piece of it. But use the arrow notation. I didn't take off if you did this, but you definitely want to use the arrows in general. Okay, when you write C code and you have something like quote W17, the compiler says, aha, this person wants to make a string W17 and set code level to point to that. So it will find a location in memory where there's 4 bytes available, and it'll store a W, a 1, a 7, and a null terminator. And then the address of that W, that's what code arrow level will get set equal to. Okay, so the compiler, actually the loader, when you link this stuff into an executable, sets up that block in memory, and code arrow level will point to it. So some people tried to do this, and this is the right spirit, but it will still Seg fault. And string copy goes from right to left. Okay, this is the destination, this is the source. So this is trying to copy this string W17 character by character into code arrow level. Well, remember, code arrow level was defined to be a char star. But whenever you define this, think inside your brain that level is equal to 0 or null. Okay, when you do this, you're saying level's going to be the address of a character, but it doesn't have a particular value yet. So imagine that it's equal to null. It may not be. It may be random. It may be exactly a good location that you actually want it to be, but pretend that it's equal to null. And if you imagine that level is equal to null, then code arrow level is null, and we're trying to copy W17 into memory location 0. That's a Seg fault. The only way you would avoid that is before you do this, you could say code arrow level equals malloc 4. Now at runtime, we find 4 bytes of memory. We take the address of the first byte. That's what code arrow level is. Now this says take these 4 bytes, W17 null terminator, copy them into memory starting at this address, which was the address of the beginning of this 4-byte block. That will absolutely work, but that's really what this does for you. And it has the advantage of not using a malloc, so if this is local, it'll go away when we exit from this scope, and so on and so forth. So set code level equal to x17 in some way, and then code arrow xc equals quote w. That allocates the character w, it assigns character w to the xc part, and this is different from double quote w. If I say w inside double quotes, that's a location in memory, it's an address. And it would set xc, which is supposed to be a character, to an 8-byte number, which is in a location somewhere in memory. If you use single quote w, that's basically the ASCII code of a w, returned as a single 8-bit number. That's what you want to put into a character, because characters are 8 bits. So single quotes for characters, double quotes for strings.
Did you do it without quotes?
No, because it would assume w is a variable, and it will give you a compile error. All right, the integer part's not too bad. Code arrow value equals -100. And remember, these have to be arrows because code is a pointer, right? Code dot level would assume that code was actually a struct node. It's not, it's an address. It's an 8-byte number with a bunch of 1s and Fs in it, pointing somewhere in memory. So the arrows say dereference what that's pointing to, take the value field, set it equal to -100. And then you wanted to set the elements of this array named stuff as follows. So 10 assignment statements. We'll set each element of that array equal to those 10 values. And if you did it with 10 assignment statements, that was fine. That was my bad. I should have made it an array of 1,000 integers. But that works, so I'm not going to argue with that. But there's other ways you can do it. If you can do it like this on a test and you got time to write it, it may be worth doing it like this instead of trying to figure out an algorithm. Okay, but there are algorithms you can use for this. So one algorithm would be make a loop. And here we're going less than 10 because we want to go up through and including 9. And we could say code stuff bracket I. And what's the formula? If we're storing element 0, we want 10, element 1, we want 9, element 2, we want 8. So the general formula looks like 10 minus I. And test edge cases, test the middle. So if I equals 0, this is 10, that's correct. If I is equal to 9, this is 10 minus 9 is 1, that's correct. Middle value, if I equals 2, this is 10 minus 2 is 8, that's correct. That's enough for me to believe that this will work in general. Don't need to do an inductive proof, but you could. So that's a good formula for it. Another approach some people took was to use a pair of variables. Start one at 10, and each time that you assign this equal to that variable, subtract 1 from that variable. That works great. And it's more certain than this if you're not comfortable with 10 minus I. At least one person set this element equal to 10, and then went from elements 1 through 9 and set this equal to the previous element minus 1. That's a clever way to do it. It works great. So there's different ways you can do this. But one way you cannot do it is this. Right, so that works when you're declaring an array and you're trying to give the elements an initial value. You can use curly brackets and list the elements. Or you can list a single element and it'll initialize everything to that value. But at runtime, that doesn't work. Because at runtime, all it's got is a variable pointing somewhere in memory, and it doesn't really have the ability to write the code necessary to do all of those assignments. You need some kind of loop, basically. When you're declaring a variable, and you're saying I want it to be equal to this set of values, that's a compile time thing. The compiler can actually arrange, in addition to saying where those things are going to be stored in memory, it can say, oh yeah, and when the program's ready to start, drop these values into there. Okay, it's a feature of C and of the linker loader. But it doesn't work in general. And it doesn't work at runtime. All right, so any questions on that? All right, everyone's favorite, the linked list. Yay. Yeah, they should make a candy bar. Actually, Sentinel would be a better name for a candy bar.
One candy bar would lead to another candy bar.
Yeah, it's bad situation.
Would that be like blackberry bars?
Yeah, or Ruffles potato chips. All right, so I mentioned during the exam on the board, right, 99 is the Sentinel node. So LL is the address of the Sentinel.
It's spelled that,
Ah,
So when we're talking about that,
Mhm.
you say not to use any loops or conditional statements.
Mhm.
So is it this specific?
that specific one, yes.
So I don't have to worry about checking for anything at
Nope.
all? Just,
No, it's
okay.
that particular list.
That's all.
Yeah,
Okay, perfect. Thank you.
yeah.
Got this. I got everything.
Yay. All right, so LL is the address of the Sentinel node. Okay, so that's a 99. So one way to think about this is LL is the address of this box. So if I want the address of this number 99, that's LL arrow data, the thing pointed to by LL, the data field. And this box down here is LL, the thing pointed to by that, the next field. LL arrow next is this value. It's an address. It's the address of this block. So if I want the data value here, that's LL arrow next, arrow data. And this address down here is LL arrow next, arrow next. And you can keep going. This block here is LL arrow next, arrow next, arrow next. And if you don't like all those arrows, there's a different way to do this. We could name these nodes. We'll play with that next. But thinking about this, so part A says what's printed by the following statement, LL arrow next next data and LL arrow next data. Well, next next data, so this is LL next next, right? So LL next next. Arrow means the thing pointed to by this, which is this block here, and arrow data means pick off the data field. So this is equal to 14, and LL next data is equal to 12. So when you print those two, you just get 14 space 12. All right, part B says write some C statements to delete the last node of the list without using loops or conditionals. Well, do we know the address of that last node? But do we have an expression that's equal to the address of that last node? Yeah, LL arrow next next next. That's this field right here, which by the construction of the linked list has the address of this node. So if I say free LL next next next, that will release this block of memory, send it back into the heap. I'm not done because right now this 14 node is pointing to that location in memory which we've just released. So we don't want to follow that. To make this node actually deleted from the list, we need to change this to be a null. And we know what this box is. This is LL next next next. So if we set that equal to null, that actually removes the 8 from the list, or it terminates the list at the 14. So there's at least two things here that can get really confusing, okay? The first thing is this question of freeing before we set this thing equal to null. And sometimes freeing something too soon is a bad thing to do. Here's where this would be a bad thing. If we were going to use this 8 or this null, we got to do that before we free this chunk of memory. Once we free this chunk of memory, we can't get to the 8 or the null anymore. Doesn't matter if we saved its address in another variable. Once we free this block, consider those values corrupted. This is now a 743 and this is a hex 42 or something, right? They're no longer accessible to us. But in this case, that's not what we're trying to do. We're not trying to access this field or this field. We're just trying to change this, which used to have this address. We're trying to change it to have an address of null. The fact that after we free this, it's pointing to something that's inaccessible to us doesn't bother us, right? We're not trying to do anything with this value or with the thing it points to. We're just trying to set this value to null. So that's perfectly fine. But if it makes you uncomfortable, we could do something like struct node star temp equals LL next next, next. And then we could set LL next, next, next to null, and then we could say free temp. And this is what most people did. And there's nothing wrong with that. I think it's probably good practice to free after you're done with everything else. And it's just a temporary variable you used. No harm done. But that's one thing that's potentially confusing. The other thing that I personally found very confusing when learning this stuff is this difference between when we say this is LL next. Is LL next this or is it this? Right? And that can flip, if this makes sense to you, cover your ears because I don't want to confuse you. But it can flip around sometimes. Sometimes LL next is the value here, and sometimes it's actually this node. And it's a little bit of sloppiness or casualness in terminology, right? LL arrow next actually means take the thing that LL is pointing to and look at the field called next. The thing that LL is pointing to is this block of memory. The field called next is this subblock of memory. So this is LL arrow next. But when we say something like LL arrow next arrow data, right, we're not saying the data part of LL next. We're saying the data part of the thing LL next points to. And this only makes sense because the thing that's at this block is actually the address of this block. So there's this dereferencing going on. We're saying the thing pointed to by LL next, pick off the data field. And we know that the thing stored here is the address of a struct node. So star LL next is a struct node, and we pick off the data field. And that's one of those things that until it clicks, it can flip around sometimes, but at some point it will finally click one way and not go back ever more. And if you're working with this stuff in the debugger, that can help in sort of settling these issues. Because when you print LL arrow next, right, you're going to see a 64-bit number, a 7FFFF something or another, right? And when you print star LL arrow next, you're going to see a struct node. And it's going to tell you the date is this and the next is that. Right, so that can help clarify sometimes. All right, so this will remove the 8 from there. Part C wants you to create a new node pointing to a struct node and call it new. So struct node star new. That's the declaration of a pointer to a struct node. And we want it to point to a new node, so call malloc size of struct node. Cool. Welcome. All right, so that allocates a block of memory. It sets new to be the address of that block, address of the first thing in the block. So that's a good answer for part C. And then in part D, we want to take this new node and sandwich it in between the 12 and the 14. So my picture is getting really messy. But here's our new node. Mm-hmm.
So you were talking about the whole where to place a star thing.
Yeah.
Is there like a standard in the professional world where most people do it one way?
I wouldn't know.
You wouldn't know.
Yeah.
So I put it on the variable like the new,
Mm-hmm.
and I've just been doing that the whole time. And, I mean, it doesn't confuse me, but I don't know.
If it makes sense to you, keep doing it. The reality is that when you start writing code for a large organization, you probably got code formatters that are like changing what you do anyway, and so you can type it one way and it'll change it into another way, which is a feature or a bug, depending on your viewpoint. But I don't know what's more common today. But I'll bet you could have fun, pop yourself some popcorn and go on Stack Overflow and say which one of these ways is the right way, and then just watch the fireworks. That might be interesting. Yeah. All right, so we want to sandwich this new node between the 12 and the 14. So we have to do two things. We have to make the 12 point to our new node, and we have to make the new node point to the 14. Well, if we want the 12 to point to our new node, this 12 node is LL, arrow next, arrow next. That's this block right here. We want that to point to our new node. So if we just set that equal to new, that sets up this link right here. We also want news next to point where this 12 block was pointing. In other words, we want it to point to LL next next. But we can't do that after we do this because we've already destroyed LL next next here. So before we change this to point to new, we want to take new and point where this block is pointing. So we can do that with something like new next equals LL next next. That sets up this link. And then we do LL next next equals new. That sets up that link. So it's a specific example of the general insert that you've done in linked lists. Probably 3 times now, probably 4 times now. PA1, PA2, stacks and queues. And ODPs. Yeah. And like I say, if this is not, if you're not totally at peace with the arrow, arrow next, and so on, you don't need to do that. So what can we do? Well, LL is the address of this node. We could say node 12 equals LL arrow next. Now node 12 is the address of this node containing a 12. And we could say node 14 equals node 12 arrow next. So node 12 is pointing here, node 14 is pointing here, and we could say node 8 equals node 14 arrow next. And now node 8, so declare these to be struct node stars, right, as usual. And now I've got a bunch of variables pointing to all my different nodes. And so if I want to do something like delete this last node, it's pretty easy. I say node 14 arrow next equals null, and then free node 8. And you don't have all these arrow next, next, next going around. So this to me is a lot clearer as to what's going on when you have a specific list like this. When we don't have a specific list, that's when we've been using things like previous and current, or previous, current, and next, or something like that. And if we want to make a new node, so new is pointing to our new block, and we want to put it between the 12 and the 14, so we can say new next equals node 12 next, and that sets up this. And then node 12 next equals new, and that sets up this. There's your insert. All right, so different ways to tackle this. Which brings us to queues. So queues, remember, you insert at the tail, you remove from the head. So here's the head. Here's the tail. And I wanted you to draw it out 7 times, but we'll just do it in place here. So the first instruction, so the queue is empty initially. First instruction is to insert a 10. So 10 goes into the tail. We have exactly one thing in our queue. That's just the number 10. I didn't care if you drew it over here, or in the middle. You're just showing how these things are oriented inside the queue. Next instruction is insert 20. That's going to go into the tail. It's going to go behind the thing that's already at the head of the queue. Right, so this is the checkout line. This is where new customers are coming in. This is where you're leaving the line. So the next thing is to insert a 15. That's going to go at the tail over here. And now your queue has 3 things, 10, 20, and 15. Now we say remove. We remove whatever number is at the head. That's the 10. So this comes out of the queue, and our queue contains 20 and then 15 at the tail. We do another remove. That'll remove the 20. And now we only have a 15 in the queue. We say insert 30. That goes into the tail, so it comes in behind the 15. And then we say remove once more. 15's at the head, so the 15 comes out. And now there's one thing in the queue, which is a 30. So most people did this correctly. A few people were doing a LIFO. They were putting things in and then taking them out in the same order that they put them in. Most recent for in comes out first. That's a stack. Okay. Queue is first in, first out. So the first thing you put in will be the first thing that comes out. We put a 10 in with an insert statement. So the first time we say remove, the 10's going to come out. All right, so that's queues. Question 4 was the other linked list question. So we had a list with this different kind of node, piece of data which is a character, and then a pointer to the next node. So standard linked list structure, but the data is a single character. The list has a Sentinel node, and the goal was to be able to count the number of data nodes that contain the character A. So it's basically a traversal question. You're moving through your list, and at each point, instead of printing the value of the data, you compare it to the letter A, and you keep a running count. So this looks like some of the other code you've written. So our function is called count. It returns an integer. That's the number of A's. It takes a struct node, pointer. I'll call it sent for Sentinel. And we need to keep a running count of how many A's we've seen, so we'll make a variable. I'll just call it num A and set that equal to 0. That's the number of A's. All right, so how do we start this thing? Remember, with a linked list with a Sentinel, we don't want to look at the Sentinel's data. The Sentinel itself is never null, so we don't need to check if sent is null. We really want to start working with a node that the Sentinel points to, which might be null. So we can make a local variable. I'll just call it temp. And I'll set that to the first data node. So Sentinel node arrow next. First data node, or it might be null if there's nothing in the list. Yeah?
So I kind of ran into this recently with something I was coding up, but do you avoid using the variable name next just for semantics? Like, not looking at it like as next.
I seem to have done that when we were talking about lists originally. I kept calling the next node next, and I kind of wrinkled my nose at myself because I realized that can be confusing. There's nothing wrong with it, right? The system definitely won't get confused because one's a variable name, one is a field. But if you're writing the code and you're worried about it, you could call it next node or something like that. But yeah, technically that should be perfectly fine. Yeah, and you get like next arrow next. You don't actually need a temporary variable here. I could actually use sent as a temporary variable. Because remember, sent is a local variable. And if I set sent equal to sent arrow next, I'm changing the value of sent inside here, but that's not going to affect the value that was passed to me, right? Because it's passed by value. So this statement's actually optional. I could just say sent equals sent arrow next. But no harm in being clearer about it. Make a temporary variable, struct node star, have it point to your next node. Okay. Don't malloc. So some people are still, after they do this, they're saying temp equals malloc size of struct node. Does no real harm other than wasting some memory and some time, but you're going to give temp a new value right here. So why do you assign it to a block of memory that you malloced? The only thing that's doing is creating a memory leak, really, unless you free it right after you malloc it. So we worry about, not doing a malloc because it'll give us a seg fault, right? But that's only if you have something like a struct node star temp, and then you try to use temp arrow data or temp arrow next. Again, when you allocate, when you declare a pointer, think to yourself temp is 0, temp is null. Okay? If my next statement is something like temp arrow data, that's a potential seg fault. Okay? But the solution isn't just to go ahead and do a malloc. The solution is to think about your logic. Do I really mean temp arrow data? Because what you're saying is temp is a pointer to a struct node. Now I want to see the data piece of what it's pointing to. And that's not logically sound unless you know what temp is pointing to. So either you want to create a new node by saying malloc, or maybe you want temp to point to something that already exists, like send arrow next. Okay, so it's not an automatic that any time you do this, you're going to do a malloc. And in this case, we definitely don't, because this is just a variable. We're going to give it a value in the next statement. It's going to point to the first data node. All right, well, it's possible the temp is null. If temp is null, there are no data nodes, so we don't want to do anything. We're just going to return a 0. So this will actually work nicely as a while loop. So while temp is not null, well, if temp's not null, then temp is the address of a data node, the first data node in the list. And so we want to check its value. So if temp arrow data equals the character A, then increment the number of A's. And then move down the list, so temp equals temp arrow next. And just keep looping.
Would it be a problem to have an integer that's keeping track of the number of A's called count, since the function is named count?
No, that shouldn't be a problem.
Okay, I avoided doing that.
Yeah. No, it shouldn't get confused about that either. I'm not 100% sure of that. But I'd be surprised if it got confused. Because functions always have parentheses after them. So it can tell the difference. All right, so once we get through here, just return the number of A's. And we're done. All right, check the edge cases. So the first edge case is we want to make sure the first time through we're looking at the first data node. If we start off with temp equals sent, then the first time through we're looking at the Sentinel node's data value. That's a no-no. Okay, we want to skip over the Sentinel node. That's what this is doing. So the first time through here when we say temp arrow data, temp is the first node after the Sentinel. That's correct. The other edge case is at the end of the list. So make yourself a little end of a list, make this null, make this temp. So temp is not null, so we're going to check this piece of data, see if it's an A, and if it is, we're going to bump up the count. And then we're going to say temp equals temp arrow next. Well, temp arrow next is over here, so temp is going to be this block. We're going to come back to the top of our loop. Well, temp is not equal to null. It's not null yet. Okay, it's the address of this block. It's not a 0. So now we're going to check temp arrow data. That's going to check this value. Adjust the count accordingly. And then it's going to say temp equals temp arrow next. Well, the next field of temp is null. So now temp is going to equal null. Go back up to the top of the loop. Well, temp is not null. That fails. We'll kick out of the loop. So we started with the first data node. We processed the last data node, and then we exited. That's what you want. Okay, there are different ways to write this. And I saw 3 or 4 variations on this, and most people got them right, even if they were doing something different, and that's great. Okay, this is not the magic right one way to do it. Okay, but some variations you can do. For example, you can start off with temp equals sent and say, well, temp arrow next is not null, and then check temp arrow next arrow data, and that works fine. Or you can start off with temp equals sent and say, well, temp is arrow next is not null, set temp equal to temp arrow next, and then check temp arrow data. And that also works. But there's slight tweaks on those that will either count the Sentinel's data or miss the last data node. So either starting too early in the list or exiting too soon before you actually check the last node. And in some cases, after the while loop is done, there was one more line of code checking that last node, and that's fine. So there's different things you can do. But in your head, right, especially when you're doing this on a programming assignment or something calmer than a test, right, think about the edge cases. Go through it the first time, make sure it's looking at the first node. Run through it the very last time and make sure it picked up the last node, and then it exited. All right, we can get through the rest of this and then take a break, because the rest are pretty straightforward. So the stack question. So I gave you the code for push and pop. You didn't have to know anything about stacks to do this. But if you understand how stacks work, that can help you work with this code more quickly. But remember, stacks, there's multiple ways we can implement a stack. Pre-increment, pre-decrement, post-increment, post-decrement, right? So I gave you the code here. That tells you exactly what a push and a pop does. And in your mind, if you're comfortable with stacks, you can say, okay, this is a post-increment push and a pre-decrement pop. And then you don't have to keep coming back to the code. But the code's actually what's going to happen. So what is the push actually doing? We're saying push n, n's an integer. It's saying store n in the data array at the location given by SP, and then increment SP. So data bracket SP equals n, and then SP equals SP plus 1. And a pop is doing the opposite. It's subtracting 1 from the stack pointer and then looking at that element in the data array. So a pop says SP equals SP minus 1. And I didn't ask you to show me the value that was popped, so we don't really care what the return value is. The only effective action of a pop is it decrements the stack pointer. All right, so let's see what this does. Our stack pointer is initialized to 0. Our data array has 100 elements, so the last one is 99, but I only showed you the first 5. And these are initially unknown because there's nothing in the code that initializes these elements. Bless you. All right, so part A says push a 10, push a 20, and then push a 15. All right, so what happens when we say push 10? Store 10 in data bracket SP. SP is 0, so this becomes a 10, and then increment the stack pointer. That's the whole action of a push. If you know how to do that, you can do all these pushes. Okay, push 20, store 20 at the element indexed by SP. SP is 1, so store a 20 here, and then increment the stack pointer. Push a 15, store a 15 at index 2, and increment the stack pointer. So at the end of part A, your stack pointer is equal to 3. Your data array contains a 10, a 20, a 15, and 2 question marks. All right, part B, we want to push a 7, and then we want to do a pair of pops. So push 7 says store a 7 at the index given by SP, that's a 3, and increment the stack pointer. Got it?
Yeah.
Okay.
I started over, so.
Oh, okay. And then pop. So pop just decrements the stack pointer, and then pop again, that decrements the stack pointer. So now your stack pointer is 2, and your array contains a 10, a 20, a 15, a 7, and a question mark. There's nothing in this code that changes the elements and data when you pop. Right? We think of the value as being removed from the stack, but it's not, right? All we're doing is decrementing the stack pointer and returning to the caller the value at that index. All right, part C. We do a pop. We do a push of 7, push of 8, and a push of 6. So pop decrements the stack pointer. Push of 7 stores a 7 at the index given by the stack pointer and increments SP. Push of 8 stores at index 2 and increments the stack pointer. And a push of 6 stores at index 3 and increments the stack pointer. So now our stack contains a 10, 7, 8, 6, and a question mark. And the stack pointer is equal to 4. And then part D says push 15.
The time is
Do
1300
5 pops.
hours.
So push 15, store a 15 at index 4, increment the stack pointer. Pop says decrement the stack pointer. This says decrement the stack pointer. This says decrement the stack pointer. This says decrement the stack pointer. And this says decrement the stack pointer. So now stack pointer is 0, and your array contains 10, 7, 8, 6, and 15. All right, and then question 6. So abstract data types, right? A queue is an abstract data type. We're not interested in the implementation details. See down here, this is how we implement a remove function. Remove from the head, we increment the head index, and we roll it over at 1,000. So if we had an array of 1,000 elements as a circular queue, and we were using head as the name of the variable that tells us where the head is, this would be the remove instruction. But that's not part of the abstract definition of a queue. There's nothing in the definition of a queue about the number 1,000, about the modulo operator, about incrementing a head, right? Removing from a queue is just taking the thing at the head and pulling it out of the structure and moving the head to point to the next thing in the queue. So that's not part of the abstract definition of a queue, okay, whereas insert, remove, and is full are. So that's the outlier there, C. Seg Faults, did we talk about this one? No, yeah, we did. So, so B is the one that could potentially do a seg fault. Integer star x, imagine x is 0. Y equals star x, set y equal to the thing at memory location 0, that's a seg fault. Okay, A is just setting y to the address of x, that's perfectly legal no matter where x is. C is just adding 2 integers, storing in a third, that's always legal. And D is taking a pointer to an integer and making it point to Y. And that's a perfectly fine thing to do with a pointer. Have it point to something that it's supposed to point to, and then print the thing it's pointing to. That's just printing X.
That's where the star, where putting the star in a pointer declaration got me.
Oh, okay.
I had to come back to this problem multiple times.
Yeah, so I'm not consistent here. So when I'm pointing to a built-in variable type like a character or an int, I think I put the star next to the variable name. I don't know why I do that. But when I have a struct, I put the star next to the name of the struct. That's interesting. Yeah, I know, totally. I'll ask my dog to explain it to me. My dog thinks that he understands me. Well, the problem is you haven't fed me enough today. Okay.
Dinner number 4?
Yeah. All right, so part C, write a statement to allocate enough space for an array of 125 elements of type struct big. And I put on the board this had to be allocated at runtime. Okay, so it's a malloc statement. And you can do something like 125 times size of struct big. So this is the size of one struct big. Multiplied by 125, that's the size of 125 consecutive struct bigs. So if you have an array of 125 struct bigs, they're going to be stacked in memory one after another. So that will allocate space for it. You could also do size of struct big bracket 125. And that should work fine. But I like using size of on just like pure types and then do the math.
I didn't think you'd need the extra parentheses if you said struct big times 125, because wouldn't it just go left to right? You put the 125 on another side, that's what I did.
What do you mean?
Like I did struct big, then times 125, and then double close parentheses. Yeah.
Try it, it should give you a compile error. Because struct big star 125 is not a type of variable. Right, size of is looking for typically a type of variable, or it'll actually take a variable name and tell you how much space it needs. But, and I don't know if I tried that one or not. Let's try it. Yeah. Right, so safest thing to do when you're working with size of is only pass it the name of a variable type. Okay, you can get away with passing it a variable, but you can also get in trouble like that. Like if you have a car star that's pointing to 1,000 elements of an array, size of that variable name will still be 8 because it's a pointer. All right, what utility can you use to help detect memory leaks? Valgrind, I think everybody got that. What do you type to compile a program named main.c if you intend to use GDB to debug it? gcc-g main.c, that's enough. That'll compile main.c with debugging information, and it'll call the output a.out. You could also do -o main, and you could put the -g over here, you could put the -o main in here, you can move things around. The only thing is -o has to be followed by the name of the output file. So if you put the -o right here, you're clobbering your main.c, because it's saying write the output into main.c, and that's how you destroy your source file. So don't do that. But the main thing is the G switch. Okay, how do you make a file? Make, right? So that's what make is for. So you just say make and bang, it does it. And then part G, you want 10 bytes of data, and you want a variable already declared named PTR to point to those 10 bytes, and then you want to print a message if there's no memory available. So something like PTR equals malloc 10. So malloc looks for 10 bytes of memory, sets it equal to PTR, and then to see if it's succeeded, if PTR equals null, print out an error message. Here's one thing you don't want to do, and I saw this in some cases. So if malloc 10 equals null, print out no memory left. Otherwise, set pointer equal to malloc 10. So what's wrong with that? You're allocating 20 bytes. And just because this first malloc was not equal to null, doesn't mean that this malloc's not going to be equal to null. I might use my last 10 bytes of memory here on this test, and then set pointer equal to malloc, and now pointer is null. Right? And this happens sometimes with things like fgets, right? Someone will say, you know, fgets a buffer, and if the first character is equal to I, then do something. Otherwise, call fgets and see if the first character is equal to S. Otherwise, call fgets and see, right? And the problem is every time you call fgets, you read another line of input. Every time you call malloc, you allocate another block of memory. Okay, so if you really wanted to do this, you could say something like, if PTR equals malloc 10 equals null, and then tell it to print. And this does the malloc, takes the result, stores it in pointer, and then checks to see if that's equal to null. So that'll combine it in one line. But you can also just do it as a pair of statements. All right, so any lingering questions on that? Look it over, come and talk to me if you have questions. I have office hours from 2 to 3. Let's take a 5-minute break, and then we're going to talk about PA4. And we don't have class on Monday, so we won't meet again for a week. So I'm going to go through PA4 today with enough detail that you can get working on it.
Not knowing about my